Welcome back to the deep dive. If you ever open a global app like Uber, watch that map instantly fill up with cars all around you.
Yeah.
Well, you basically witnessed a little miracle of distributed computing. It feels so simple, right?
Yeah.
Tapping request ride. But behind the scenes, it's actually solving one of the most intense, real-time computational problems happening, well, anywhere on the internet, really.
It's absolutely true. Today, we're going to kind of peel back the curtain on the architecture that makes that possible, this kind of massive global service.
Right.
And the high-level challenge, it sounds straightforward: match a rider with the best available driver. You it quickly, do it reliably.
Sounds simple enough.
But the scale it has to operate at, that's what's truly staggering.
Okay, let's try and define that environment first. What kind of metrics are we talking about? What does the system actually have to handle every single day?
Okay, so think about this. We're talking about meeting the needs of maybe 2 million daily active customers.
2 million users. Wow.
And then you've got about 1 million daily active drivers on the other side.
1 million drivers.
And the platform itself, it's processing something like 3 million ride requests every day.
3 million matches a day.
But, the data point that really defines the complexity, the big one, is location tracking.
Yeah.
This architecture needs to handle up to, get this, 1 billion driver location updates per day.
1 billion daily updates.
Yeah, billion. Yeah.
That breaks down to needing capacity for about 300 million location updates per minute.
Exactly.
That's not just high availability anymore. That's like instant global coordination on a massive scale.
Pretty much.
Okay, let's unpack this. Let's start with that fundamental problem. If you have 1 million drivers out there and potentially 1 million riders looking, how on earth do you find the nearest driver in that huge sea of data instantly?
Well, what's fascinating here is really understanding the trade-off they had to make. When you request that ride, the system needs to find, let's say, the nearest drivers almost instantly.
Right, the top few candidates.
Exactly. Now, if you try to calculate the exact distance between you and, say, 1 million drivers using complex geographic queries every time someone tapped the screen,
Yeah, right.
the system would just fall over, right?
Yeah.
Completely overwhelmed by the sheer compute cost.
So real-time, perfect distance calculations across the whole data set are off the table. What was the engineering compromise then? What did they prioritize for speed?
They basically chose to sacrifice maybe perfect, absolute, real-time precision for just blazing speed. And they did that through geoindexing.
Geoindexing, okay.
Yeah, their solution is based on what's called a grid system. Essentially, they take the world map and they divide it up into a large but finite grid. Think of it like a checkerboard.
Okay.
And then every driver is indexed based on the specific grid cell they happen to be in at that moment.
Huh. That's actually kind of brilliant in its simplicity. So instead of searching a massive global database of 1 million drivers,
Right.
the system just needs to figure out, okay, which grid cell is the customer in? And then it only checks maybe a few surrounding cells.
Exactly that. The immediate benefit is huge. When a customer requests a ride, the system might only need to query, I don't know, maybe 20 or 30 local grid cells.
Instead of 1 million.
Right. It drastically reduces the search space, and that's the key to guaranteeing those lightning-fast response times you see in the app.
Okay, wait, I have a question there, though, a reflection point. If you're using this grid, this GeoGrid, as the index, what happens if you have 2 drivers, right? And they're almost the same distance away, but one is just inside cell A and the other just inside cell B next door.
Ah, the boundary problem, yeah.
Does the system risk ignoring the driver who might actually be technically closer just because they fell into a slightly different, maybe less prioritized cell search? How do they handle that edge case?
That's a perfect question, and it really highlights the inherent limitation of a simple grid. They mitigate that by always querying a kind of radial area.
Not just the one cell.
No, not just the single cell you're in, but also all the adjacent cells around it. That ensures they capture candidates who are right up against the border.
I see.
The main priority here isn't like centimeter level precision at this initial filtering stage. It's about filtering out the millions of totally irrelevant drivers globally really fast.
No.
That finer distance calculation, that comes a bit later in the ranking step.
Gotcha. That makes sense. Filter first, refine later. Okay, let's circle back to that other huge number, the 1 billion location updates per day. That massive data fire hose.
Yeah, that fire hose.
If a driver's moving, are they just constantly pinging the system? GPS updates every second. Because that sounds like an unbelievable drain on bandwidth and battery life, too, for the drivers.
Right. It would be.
So what's the optimization strategy there? How do they keep the data fresh enough but still manageable?
The primary goal really is minimizing all that data overhead. They only want to update the location if it's actually, necessary for the matching process. So no, they don't update constantly.
Okay.
The system only sends a new update if one of two conditions is met. Just two.
What?
Okay, so the first condition is distance. Pretty straightforward. The driver has to have moved a significant distance from their last reported location.
So if they're stuck in traffic or just waiting at a light.
Exactly. The system conserves resources. No point sending redundant pings if the driver isn't really moving relative to potential riders.
Makes sense. And the second condition, I guess that's crucial to stop the location data getting totally stale if the driver is just sitting there for a while.
Precisely. You need a backstop. So the second condition is just a strict time limit. Even if the driver hasn't moved an inch, their location must be updated once a maximum time threshold is reached.
And how often is that?
The source material suggests it's roughly every 3 seconds. So it's this combination. Moved a significant distance or our 3 seconds have passed.
Right.
That keeps the data fresh enough for accurate matching while saving just massive amounts of compute power and network capacity.
Okay, I'm still slightly reeling from the 300 million updates per minute capacity needed on the receiving end for the system to ingest all that.
Yeah, it's intense.
Now let's flip it. Think about the customer side. I open the app, right? And I see all those little car icons moving around smoothly on the map in real time. How does that massive data pipeline sort of reverse course to efficiently broadcast those nearby driver locations back out to me?
Yeah, that's another key piece. This is where they chose what's called the push model for delivering that data. They decided against more traditional web methods like, say, HTTP long polling.
Why the push model?
Well, when you open the map, the system figures out which grid cells are relevant to your screen view. Then, instead of your phone constantly asking anything new, the server actively pushes the location updates for drivers in those cells directly to your app. It's like a continuous stream.
So the server initiates the updates.
Right, and it's just significantly more efficient for this kind of high-frequency, real-time data. Less overhead, faster updates.
And speaking of efficiency, I assume the size of those update packets has to be tiny.
Oh, absolutely critical. The efficiency is baked right into the packet itself. That location update packet, it's intentionally minimal. We're talking only 14 bytes per driver location update.
14 bytes? That's tiny.
Super tiny. And because the system sends those updates, say, every 3 seconds, like we discussed,
right,
they calculate that the required bandwidth to show you all those little moving cars on your map is only about 1.4 kilobytes per second per customer.
Wow, 1.4 kb per second. So showing millions of users these seemingly real-time car movements, the cost boils down to something like sending maybe one tiny email every few seconds.
That's a good analogy, yeah. It's that level of staggering efficiency. And that's what allows them to scale this feature to millions of simultaneous users without the costs just exploding.
That really drives home the point.
Yeah.
These huge architectural decisions, when you're operating at massive scale, they often come down to making that smallest unit of data transfer just as lean and efficient as humanly possible.
Yeah, it's the core insight right there. Absolutely.
Yeah. Okay, so we've covered the GeoGrid for fast indexing and this optimized push model for broadcasting locations efficiently. Now, the moment of truth, the actual ride request workflow. I tap that button on my phone. Where does that request actually go first?
Okay, so it leaves your phone, and the first thing it hits is a load balancer. Standard practice, really.
Sure, distributes the traffic.
Exactly. Keeps things balanced across their infrastructure. That load balancer then routes your request to one of potentially many aggregator servers. And this aggregator, think of it as the conductor for the whole matching orchestra.
The conductor. Okay, so the aggregator doesn't hold all the driver data itself, right? It's more an orchestration layer.
Precisely. It's coordinating the effort. So what it does next is pretty complex, using that geo-indexing grid system we talked about.
Yep.
The aggregator server first very quickly identifies the, let's call them the K-relevant driver servers, the ones responsible for the drivers in the local grid cells near you.
Got it. Finds the right server shards, essentially.
Exactly. Then it fans out your ride requests simultaneously to all of those relevant driver servers. And it does this using a protocol called Thrift.
Thrift. That's not a household name like HTTP.
Yeah.
Why Thrift specifically here?
Good question. Thrift is crucial here because it's a high-performance framework. It's designed specifically for this kind of inter-service communication in big distributed systems.
Oh.
It allows the aggregator to talk really quickly and efficiently to many different driver servers at the same time without huge network overhead and gather their responses super fast.
Okay, so it blasts the request via Thrift to the servers handling the nearest drivers. What do those driver servers do then?
Those servers then check the specific availability of the drivers they manage. Basic stuff, but critical. Is the driver actually logged in? Are they already on a trip? Are they even accepting requests right now?
Right. They need to be actually available.
Yes.
Yeah.
So those nearest available drivers, or rather the servers managing them, essentially respond back to the aggregator. Kind of like they're bidding for the ride saying, yep, I'm available.
Okay, so the aggregator collects all those yes responses. Now, here's where it gets really interesting, I think. The system needs to do all that, find nearby available drivers, and then decide who actually gets the ride offer. Because just being the absolute closest physically isn't always the best match, right?
Exactly. You nailed it. Proximity is just like the entry ticket to the competition.
Huh.
To ensure, good service quality and a good experience for the rider, the system relies on a pretty complex ranking component. It takes those available nearby drivers and orders them before the aggregator sends out the final match request to the winner.
And what goes into that ranking? It can't just be distance again.
No, definitely not.
Yeah.
They look at 3 critical factors, primarily.
Okay, let's break those down. Why does simple proximity need help from other metrics?
Okay, so first, naturally, is proximity. How close are they geometrically speaking? That's still important, obviously.
Sure.
Second, they factor in something like popularity or relevance. This often means weighting drivers based on things like their rating.
Ah, driver rating. Makes sense.
Yeah, or maybe their past success rate in accepting trips quickly, or other metrics that are designed to basically increase the odds of a successful, high-quality ride actually happening.
Okay, proximity, relevance, rating.
Mm-hmm.
What's the third critical factor? This must be the really dynamic one.
It is. The third, and maybe the most critical real-time calculation, is the estimated time of arrival, or ETA.
Ah, the ETA. Crucial.
Absolutely crucial, because pure proximity, the straight line as the crow flies distance, it's almost useless if the technically newest driver is stuck behind, say, a massive highway barrier.
Right, or going the wrong way on a one-way street.
Exactly, or facing the wrong way, and it'll take them 20 minutes just to get to the nearest U-turn to head towards you. The ETA calculation pulls in heavy real-time traffic data, road network conditions. It's a much more powerful predictor of how quickly that driver can actually reach you.
Okay, so putting it together, proximity, found quickly using the GeoGrid, gives you the initial candidates. Then ETA, using real-time traffic, filters those candidates based on actual road conditions. That ensures the customer gets a match that's not just close, but realistically fast.
Precisely. It balances speed of matching with the reality of the road.
But, for a system that relies so heavily on all these components talking to each other instantly, aggregators, driver servers, databases, what happens when something inevitably breaks? A server goes down, a network connection drops.
Yeah, failure is inevitable in distributed systems. So fault tolerance has to be absolutely paramount. If this service stops, even for a few seconds, millions of users are immediately impacted. Lost revenue, bad experience.
So what's the strategy? Redundancy.
Redundancy is key. Their strategy mandates really strict data redundancy at pretty much all levels. Every piece of critical data, think driver status, is someone on a trip, payment details, it must be stored on both a primary and a secondary copy.
We get primary, secondary copies.
Which allows for basically instant failover if the primary system hiccups or fails completely. The secondary can take over immediately.
And what about bigger failures, like a whole data center going offline?
Yep, they plan for that too. Geographic resilience. They replicate all this critical data across multiple data centers, often spread out across the country or even globally.
Right, so a fire or flood in one region doesn't take down the whole service.
Exactly, it's vital. If a regional outage could be power failure, natural disaster, whatever takes out an entire data center, the main load balancers automatically redirect all the traffic to another geographically separate data center. Service continues, hopefully seamlessly for the user.
Wow. That was a really fantastic deep dive. We kicked off by just trying to grasp that almost impossible scale, the 300 million updates per minute.
Yeah, the big numbers.
And we ended up understanding how that smooth, seamless user experience you get in the app is actually built on top of these incredibly deliberate, sometimes counterintuitive architectural choices. I think the key insight for me was seeing how they strategically sacrificed that absolute up to the nanosecond precision for bandwidth efficiency, like with the 3-second or distance rule for location updates.
Right. A calculated trade-off.
And how they prioritize raw search speed using that really elegant geoindexing grid system to just cut down the problem space immediately.
Yeah, I think the fundamental takeaway really is that this entire massive architecture relies on all these distributed pieces making hyper-local, super-fast decisions, but all while somehow maintaining a single definitive source of truth for location and availability across the globe. It's quite an achievement.
Absolutely. Which brings us perfectly to our final provocative thought for you, the listener, to consider. We just detailed how that aggregator server uses the GeoGrid to instantly find the absolute nearest driver candidates based on precise location data.
Yep, finding the closest ones fast.
But for user privacy and driver privacy too, Uber has to keep the identity of that driver hidden, anonymous, until the match is actually confirmed and accepted.
Right. You don't see who it is until they're on the way.
So here's the tension. If speed and proximity are absolutely everything for the initial filtering and ranking, how does that aggregator system efficiently prove proximity and rank those drivers based on location, without actually needing to know who they are until the very last moment when the transaction is locked in? How do you balance that need for speed using location with the need for anonymity? That's the real engineering puzzle, isn't it? That tension between speed, proximity, and privacy, all within the same high-speed matching system.
That's a great question to ponder. How do they square that circle?
Something for you to mull over until our next deep dive.